Lecture 9, Semi-Parametric Models. Now in this lecture, we're going to look at the modelling of fundamentally nonlinear relationships. The lecture is split into 8 parts. As usual, I'll begin by outlining the learning outcomes, and we're then going to look in part 2 of the lecture at how we can model nonlinear relationships via the usual linear imparameters framework. We're going to look at polynomials, which we've seen before, and I'm going to then introduce step functions. In parts 3, 4, 5, 6 and 7 of the lecture, we're going to look at various forms of what's called semi-parametric modelling. And these are models that are more flexible than we can achieve by simply innovating within the standard linear imparameters framework. And then in the final part of the lecture, I'm going to summarise what we've learned. So let me just outline the learning outcomes for this lecture. Following this lecture, I want you to be able to explain the concept of a semi-parametric model. So what does that mean in the context of nonlinear modelling? And I want you also to be able to provide a motivation for why we should be interested in these kind of flexible models. I want you to be able to distinguish between a linear imparameters model form and a form that's the form we've been dealing with up till now. And I want you to be able to distinguish that from models that incorporate what we're going to call a non-parametric element. I want you to be able to write polynomial and step function regression models in their linear imparameter form. And then turning to the semi-parametric models that we're going to cover, I want you to be able to explain the 3 components of these models, that is basis functions, splines and knots. You should be able to construct regression splines, that is to write down the mathematical form of these splines using knots and truncated power basis functions. And you should be able to calculate the degrees of freedom for regression splines and for natural splines. We'll then next talk about what's called smoothing splines that have a form in which there's a loss plus a penalty. That's the formulation. And I want you to be able to describe smoothing splines and understand the role that the so-called smoothing parameter lambda plays in these models. And I also want you to understand why these or how these smoothing splines differ from the regression splines that we talk about beforehand. Next, we'll talk about local regression, and I want you to be able to write down an algorithm that can be used to implement this method. We'll then talk about generalized additive models, and I want you to be able to understand how we can use these so-called GAMs to account for nonlinear relationships when we have multiple covariates. And throughout the lecture, we're going to use examples to demonstrate these methods in R. So at the end of this lecture, you should be able to execute the approaches that we've discussed for semi-parametric modelling using R software. So this lecture is all about non-linearity. That's what we've called this slide here, moving beyond linearity. And so far we've covered a variety of models in this course, all of which have attempted to represent a relationship between a dependent variable y and a set of independent variables that we've denoted x1 up to xk. But in all cases, what we've sought to do is model the conditional mean of y, that is mu, or some function of that mean, g mu, as in the case of a GLM, this could be a link function. We've modelled it using a parametric linear predictor. That's what we've called it, a linear predictor. Now this linear imparameters assumption that we've talked about so many times that's embedded in these approaches is actually very flexible. However, it can provide a poor approximation when we're trying to model relationships that are really significantly nonlinear. And in this lecture, we're going to introduce techniques that deal with those settings, that deal with settings in which there is significant nonlinearity, and we're going to use flexible techniques that allow us to move beyond linearity, but that do so without compromising the ease of estimation and don't compromise the interpretation of the models themselves. And we're going to call these models semi-parametric. And we call them semi-parametric because they combine elements from parametric models and from non-parametric models. So by a parametric model, what we mean is that a specific functional form is assumed based on a small set of parameters, and that is implemented within the linear in parameters framework. In a non-parametric model, we don't a priori assume a functional form via a parametric form. Instead, we introduce a flexibility in modelling that allows us to model the functional form via a larger number of parameters than we would usually use in a parametric model. So in other words, the functional form is essentially going to be determined from the data in a non-parametric model. We're not going to assume it via a parametric form. We're going to use a large number of parameters to determine the form from the data. And semi-parametric models combine elements from these two approaches. Now I want to state here that this terminology of non-parametric, semi-parametric and parametric is actually somewhat misleading. Semi-parametric models, non-parametric models and parametric models actually all do involve parameters. None of them can be formulated and estimated without parameters. But with non-parametric and semi-parametric models, we're using the parameters in a less prescriptive way than a purely parametric model does. And that's the point, is using a larger number of parameters to induce flexibility. And I hope this will be evident as we proceed throughout the lecture. So we're talking about semi-parametric models which combine elements from parametric and non-parametric approaches. And it turns out that these models can be specified and estimated in ways that are going to be familiar to us. So they can be estimated via least squares, via maximum likelihood, and via REML. So actually in this lecture, we're not really going to need to say much about estimation theory. We can use the estimation procedures we've seen in previous lectures and just continue with them. This lecture actually is much more about the style or the approach to modelling, so to speak, the flexibility, the idea of designing a model flexibly, specifically in order to incorporate non-linearities. So the way the lecture is structured is, we're first going to consider two parametric model innovations that we can use to model non-linearities within the usual framework that we've seen so far, that is, the linear in parameters framework. So we're going to look at polynomial regression, which actually we've already talked about, and we're going to look at step functions, which we'll introduce today. And these two linear and parameter innovations, let's call them, are actually important as a precursor to discussing semi-parametric models. Because semi-parametric models are essentially going to combine these two elements to produce a flexible functional form for model fit. That's the principle. So having seen these two linear and parameter techniques, we'll then consider semi-parametric methods. These are more complex, flexible models that incorporate a non-parametric element by introducing a larger number of parameters. And I say more complex models, they're not intellectually more complex, they're actually quite simple. They're just more complex in the form that they take. And again, this will be evident as we move through the lectures. So we're going to talk about regression splines first under semi-parametric models. There's various different types of regression spline we'll look at. So that will be quite a large part of the lecture. We'll then talk about smoothing splines, which are still a spline-based approach, but distinct from regression splines. We'll then move on to look at local smoothing, which is quite a different approach. It's not a spline-based approach to scatterplot smoothing, sometimes called local regression. And finally, we'll look at generalized additive models, which are applicable where we want to model nonlinear relationships across multiple covariates. So we're going to begin our discussion with an exposition of approaches that extend the linear regression model. And we're going to look at just the simple regression in which we've got a continuous response and one single covariate, so just one independent variable. And the reason we're going to do that is because our interest here isn't in principle looking at multiple covariates. That doesn't really add much to what we're talking about. We're interested in representing nonlinear relationships, so we'll keep things simple and focus, and we'll look at a single nonlinear relationship between a dependent variable y and a single covariate x. And in that setting of the simple y and 1x, we can provide an illustration of all of the main concepts that we're interested in talking about in nonlinear modelling. But of course, in the last part of the lecture, when we introduce these GAMs, we will extend things to the multiple covariate setting.